Hello everybody, welcome to the fourth and final video in Unit 1, an introduction to machine learning. This video is going to discuss the essential math competencies to machine learning and artificial intelligence research. Going in, it's essential that we have a mathematical background so that we can understand how and why algorithms are structured the way they are. So let's dive right in. The first thing we're going to talk about is multivariate calculus. Calculus is the best math we have to talk about smooth changes. And when it comes to machine learning, this is happening constantly. When we have optimization problems, what we're really trying to do is minimize the error. And we do this by using derivatives and gradients. When we're doing probability measurements, we're going to do integrations to sum up the weights and get our probabilities. So we're using both derivatives and integration in a variety of different settings. But let's go ahead and dive in and see some of those actual examples. So the first would be our optimization via gradient descent. Gradient descent is actually how we train all of these models to optimize their parameters. So here we minimize the objective function, whatever the objective function may be. Typically it's going to be your error. So we're trying to minimize error here, if that would be our objective function, over our model's parameters. Eta here, the Greek symbol, is going to be the learning rate, and it's going to determine the step size of our actual gradient descent. So when we start getting into the parameters that these functions use, such as learning rate, understanding the math behind the algorithms is going to help you optimize the different settings in the most appropriate way. So when you're adjusting learning rate, it helps to understand gradient descent so that you can adjust that value appropriately. And this is essentially just trying to find a local minimum using our error equation to the left. Again, we have the gradient, and the gradient is built up of derivatives, so it's important to know multivariate calculus so that we can do this math. Furthermore, this problem becomes much more difficult when you have a high number of inputs, and theta here, our parameters, are many, because then you're working over high dimensions as well, and it's harder to visualize this conceptually. So you have to have a good background in the math so that you can understand how to do optimization problems. We're also going to use integration to find probability calculations. So in most of these problems, we're going to get probability density functions, and this is essentially just a distribution of the probabilities, and we can find the total probability by integrating over a certain range. Integrating over the entire range is going to give us 100% or 100% chance of that happening. Integrating over a particular range is going to give us a smaller probability. So it's important to know integrals because these probability density functions are often going to be solved via integration. So let's talk about another example of that, and this is in Bayesian inference. So this is a statistical inference in which Bayes' theorem, which we're going to talk about, is used to update the probability for a hypothesis as more evidence or information becomes available. So let's go over this. We have a data set, and we can use Bayes' rule, which we will go into in a later slide in more detail. However, what Bayes' rule often gives you is a posterior distribution, and solving this distribution is known as the inference problem. And as you can see, we have an integration over d theta, and theta here is going to be our parameters. So when you have many parameters, this isn't just a single integral. It can be a double, triple, all the way up to however many parameters we have. And solving this integral can get very difficult because of its high dimensional nature. So Bayesian inference is something that you should understand as well, and solving the integrations on the posterior distribution is going to be one of the main reasons that you need to know multivariate calculus. But this is actually a good segue into the topic that we're going to talk about next, and that is probability theory. So statistics and probability theory is absolutely essential for machine learning and artificial intelligence. We need statistics to deal with uncertain events. That's what we're trying to do in almost every scenario in machine learning. We also need statistics to develop mathematical formulations for probabilities. We saw our posterior distribution in the previous slide. This is going to be a mathematical formulation for probability, and so solving that is going to be based in statistics. We also needed to estimate probabilities from data. All of this, again, is based in statistics and probability theory. But we can probably understand this better if we actually dive into an example. And so we're going to come back with Bayes' rule, and this is really modeling dependence and conditional probability. So this is the assumption that knowing X will tell us something about Y. Or perhaps we could say knowing something about previous data will tell us something about the future. Again, this is what machine learning is based around. So in this scenario, we have the probability of Y given X times the probability of X is going to be equal to the probability of Y and X. And again, that is equal to the probability of X given Y times the probability of Y. And solving that, moving some things around algebraically, is going to give us Bayes' rule. That is the probability of X given that we know Y is going to be equal to the probability of Y given X times the probability of X divided by the probability of Y. So that's a lot of words and letters and variables that is explained better through an actual example. So let's use that. We're going to do an AIDS test. How likely is it to have AIDS if you test positive? It seems pretty likely, doesn't it, if you're testing positive? But let's actually see. So we're going to start with a couple assumptions here. Roughly 0.1% of the population is infected with AIDS. So we have the probability of X equals AIDS is equal to 0.001. This is 0.1%. Our next assumption, the test reports positive for all infections. If you have an infection, 100% of the time you are going to be testing positive. So we have the probability of Y, test positive, given that X, you have AIDS, is equal to 1. Our next assumption, the AIDS test reports positive for 1% of healthy people. So we have some false positives here in this test. 1% of the time it's going to say you have AIDS when you actually don't. So the probability of Y, test positive, given that you are healthy, is equal to 0.01. So let's plug this into Bayes' rule to find the probability of AIDS given that you test positive. This is the probability of X given that Y, you're testing positive on this test. So here's the formula again for Bayes' rule, probability of X given that Y, and plugging in our actual, or solving first, and then we can plug in our actual numbers. We have the probability of Y given X and the probability of X. Those are from above. This X over capital X on the bottom here is just going to be inverse. So instead of 0.01 or 0.001, we have 0.999. And so this is going to spit out 0.091. There's actually only a 9.1% chance that if you test positive, you actually have AIDS. So Bayes' rule is telling us something here that is probably counterintuitive. And this is why having a strong understanding of probability theory and statistics is essential for machine learning, because oftentimes the outputs and probabilities are going to be counterintuitive. So it's essential to understand that going in. However, let's continue on this example and improve our inference by following up with an additional test. So what we're going to do is perform a follow-up with an independent test. It's independent to the first one, which has the following properties. Second test reports positive for 90% of the infections. So if you have an infection, 90% of the time it's going to catch it. The second test reports positive for 5% of healthy people. So we have a slightly higher false positive rate here for this second test. Here we're going to add this into our formulation of Bayes' rule in the previous slide, and we simply have the additions of the 0.05 highlighted in red here and the 0.9 into our formula that we had written out before. And all of a sudden, our chances of actually having AIDS go up to 35.7% from 9%. So it's increased significantly by having an additional data point. So what we can conclude, adding extra observations can improve the confidence of the test considerably. So extra observations in machine learning are going to be additional tests or data points. And this is why having large data sets is essential to developing good algorithms in machine learning. Each additional data point that you have improves your inference significantly. And when we're inferring knowledge from data, this is everything. So let's do a quick mini summary. Probability theory is used to model uncertain events. Dependence and independence is what we end up exploiting for estimation, which leads us to Bayes' rule. And finally, prior probability matters, the prior probability of AIDS in our example. And then combining tests improves outcomes significantly. But let's move on. Our last core math competency is going to be linear algebra. And this is a branch of mathematics that lets you concisely describe coordinates and interactions of planes in higher dimensions and perform operations on them. We were mentioning in previous videos, as soon as we add additional inputs, we're getting into a higher dimension. If we have 2 inputs, that's 2 dimensions, 3 inputs, 3 dimensions, 4, 5, etc. Some of these algorithms are going to have hundreds, if not thousands, of inputs. When we're thinking about an image, even a 16 by 16 matrix 8-bit image is going to have 256 different inputs. So doing math in 256 dimensions is going to be impossible without an understanding of linear algebra. So why linear algebra? First, it's a foundation field. So a lot of the calculus and the probability theory is going to use linear algebra, if not just linear algebra notation, in its formulations. Also, matrices and vectors are how these algorithms are represented. Our inputs are going to be matrices or vectors, and our outputs are also often going to be matrices or vectors as well. And again, we have high dimensional representations of the data. When we are working in higher dimensional space, it's important to use linear algebra to solve and perform the operations that we need to on the data. So we're solving in high dimensions and we're using the linear algebra to perform those operations. And again, we have the notation. This notation is used almost exclusively in machine learning as well as in many other areas, so it's just good to know because so many other maths are based on it. So here, this is just matrices and vectors. We have scalars, vectors, and matrices. If this doesn't look incredibly familiar to you, I would highly encourage doing a quick crash course on linear algebra before getting started. So a scalar, we just have one numerical value, while a vector, we're going to have a row vector or a column vector, which is going to be a set of those scalars. And then a matrix is expanding that to 2 dimensions. Here you have a row times column. The indexing in matrices is going to be incredibly important. Again, this is just a 2-dimensional matrix. We're going to get up into high dimensional structures where the math becomes unintuitive. So understanding linear algebra and how it relates to the other core math competencies like probability theory and multivariate calculus is going to be essential going in. So here's the minimum linear algebra that you should know for machine learning. 1, the most essential is notation. Understanding the algorithm structure as well as the input and output structure is going to be impossible if you're not at least familiar with the notation used in linear algebra. How does indexing for a matrix work, for example, is going to be something that you need to know in order to understand how to feed data into these algorithms. Notation is going to be essential even if you're not trying to develop your own algorithms. Even just applying an algorithm that somebody else has built, you're going to need to know notation. It's also going to be incredibly helpful to know linear algebra operations. When we're working at the next level of abstraction in the vectors and matrices, learning to apply simple operations like adding, multiplying, inverting, transposing, etc. on these matrices and vectors is going to be necessary. So these operations are used a lot, and so understanding them before going in is going to help you apply and use these algorithms efficiently. So here we have a quick summary. The 3 keys. 1, multivariate calculus. You got to know calculus because we're working with smoothing problems, optimization problems using gradient descent and error minimization, and we're also doing summations and integrations when we're solving for our probabilities. You have to know probability theory because, again, machine learning is based in statistics. So understanding statistics and probability theory is going to help you understand the why and the how these algorithms are working. And finally, linear algebra is necessary because most of our inputs and outputs and the actual algorithm structure itself is going to use linear algebra notations and use linear algebra operations. When we're working in high dimensional spaces, the only way to do this is via linear algebra. If you want to learn more, you can check out some of these recommended resources. 2 great books that are available online. You have The Information Theory, Inference and Learning Algorithms by David McKay. That one goes over a lot of the probability theory that is going to be important to this machine learning research, as well as The Elements of Statistical Learning by these 3 authors. It's an incredible book that goes into a lot of the stuff that we're going to cover in this class, but also dives into the math behind it so that you can understand why these algorithms are working the way they do. All right, everybody, thank you for listening to this 4th and final video, the Essential Math Competencies. This is going to include Unit 1, our Introduction to Machine Learning. So you should have a basis now to understand what is machine learning, the types of machine learning that are out there, and in Unit 2 and 3, we're going to dive into the specifics. So Unit 2 is going to cover supervised learning, so we're going to learn a lot more about classification and regression algorithms, the math behind them and how they work and where they should be used. In Unit 3, again, we're going to dive into the unsupervised learning, and this is going to cover clustering, how that works, as well as have a section on reinforcement learning, since it kind of falls under that unsupervised category. Thanks again for listening and following along.